In this video, I'm going to explain some of the key algebraic properties of logarithms. First, I'm going to show you the graph of 2 to the x, and then show you a few things about this function 2 to the x. So, first of all, get this picture in your head, and then I'm going to take these numbers and write them on a number line. So let me show you this. Here's my number line. Here's my x numbers. So -3, -2, -1, 0, 1, 2, 3, 4, and so on. So the numbers underneath are just an ordinary linear number line. And then up above that, I've written 2 to the x. So above 0, I've written 2 to the 0, which is 1. Above 1, I've written 2 to the 1, which is 2. 2 to the 2 is 4, 2 to the 3 is 8. 2 to the -1 is a half, 2 to the -2 is a fourth. So that's where this big long line of numbers comes from. Now I want you to remember that exponents have a number of algebraic properties, and among them is this one. I've done it specifically with base 2 here, but 2 to the m plus n is 2 to the m times 2 to the n. Now let me show you a way of seeing this with the number line. So first, let me move this over. The green thing there is of length 3 in the units that I'm using for this picture. And the blue one is 2 units. So you can see there, just so that we have this, 2 squared is 4, and 2 cubed is 8. Now 4 times 8 is 32, which is 2 to the 5th. And there you can see 2 and 3. 2 plus the 2 there, the 3 there, add together to give this 5. And I can see that visually because I can slide this over, and you can see here 3 units in green, plus 2 units in blue is 5. But then up here, I've multiplied effectively 8 by 4. Undo. So there we go. 8 times 4 is 32. I could also do, for example, move this out of the way and erase this. 2 to the 3rd is 8, and 2 to the 4th is 16. Well, I don't really know what 8 times 16 is off the top of my head, but I know it should be 2 to the 7th, right? Because I add the 3 there to the 4 there. And visually, I can use, come on, grab and move. So the green bracket here is 3 units wide, and the orange bracket is 4 units. If I think of this in terms of addition, I've said that 3 plus 4 is 7. But if I look up top on my exponential numbers, this is 8, and then the orange number represents 16. And I see that, 128 is my result. So that's a key fact of multiplication of things with exponents. But now let me write this out another way. The logarithm base 2 of 8 is 3. That's what 2 to the third equals 8 means in terms of logarithms. I've applied the logarithm base 2 to both sides of this equation to get that the logarithm base 2 of 8 is equal to 3. I can do the same for this equation and get that the logarithm base 2 of 16 is 4. So again, I've recognized 16 equals 2 to the fourth, and that exponent is the logarithm, the value of log base 2 of 16. Oops, I wrote 126. That's not right. It's 128. Okay, well, 128 is 2 to the 7th. Here's what happens now. The logarithm base 2 of 128 is 7, which is equal to the log base 2 of 8, that's the 3, plus the log base 2 of 16, that's the 4. So in other words, this is 7 equals 3 plus 4, and it is exactly parallel to the equation that 128 is 8 times 16. Okay, so you got to think about this carefully. 128 is 2 to the 7th, 8 is 2 to the 3rd, and 16 is 2 to the 4th. So I can take the equation 128 equals 8 times 16 and write that as 128 equals 2 to the 7th. That is equal to 8, which is 2 to the 3rd, times 16, which is 2 to the 4th. And again, what makes this work is this property of exponents, that 2 to the m plus n is 2 to the m times 2 to the n. Okay? So the key fact here is that a property of logarithms comes out of this property of exponents. Let me show you exactly what that looks like. So fast forward here. Here's what it looks like using base e. So first, I'll begin with just e to the m times e to the n equals e to the m plus n, basic property of exponents. Then I'm going to change my symbols around. I'm going to let u be e to the m and let v be e to the n. Using the inverse property of the logarithm is the inverse function of e to a power, I can go from u equals e to the m to ln of u equals m. That's going from here to here. And likewise, I can go from v equals e to the n to ln of v equals n. So that's the same kind of thing as going from top here to bottom here, just with n and v. Now I take these and start replacing things over here. So I'll replace the e to the m with u. I'll replace e to the n with v. Right, that's here and there. Then I'm going to replace the m up there with ln of u and replace the n up here with ln of v. Okay, so I've replaced the m and the n with ln of u and ln of v. So that takes me to the second equation. U times v equals e to the ln of u plus ln of v. Now again, if I have something equals e to a power, then whatever this power is, that's the result of the logarithm of this thing on the other side. So again, I've got this circle that I can go through. I have an equation like this that matches the top. I'll apply ln to both sides. So I'll get ln of the left, so ln of that left equals the thing up in the exponent here. So what that gives me finally is that ln of u times v is equal to ln of u plus ln of v. In short, ln applied to multiplication comes apart into ln of the left thing plus ln of the right thing. So it comes apart into addition. Now, it turns out that there was a very clever person way back when who came up with this idea of a physical device that could take advantage of this property. And it was a way of accomplishing multiplication by adding lengths. Okay, here's a browser program that emulates a slide rule. This is the device. The two things that you need to look at are the C scale and the D scale. So if you can see, there's a crosshair thing here. All right, come back. But that there's a C scale right at the bottom of this central part and a D scale right at the top of the lower part. I'm going to do a little bit of sliding here and show you this. So again, watch the C scale and the D scale. If you look, 2 is represented by the length from the left end here up to where the 2 is on the D scale. Now 3 is represented, well, there's the C scale, the start of the C scale, and then this length is 3. And you can see that right here, the 3 on the C scale lines up with the 6 on the D scale. What's actually going on is that the length here between the 1 on the D scale and the 2 on the D scale is the logarithm of 2. The distance between the 1 on the C scale is the same as the D scale, just drawn up above the joint. So the distance from the 1 on the C scale to the 3 on the C scale is the logarithm of 3. When you slide the central part over, like I've got it aligned here, what you're doing is adding logarithm of 2 to logarithm of 3, and you can read the result on the D scale, the logarithm of 6. So this is a tool that uses the fact that you can slide rulers around to add lengths. If you place a number at a position that's really where its logarithm would go on a linear scale, then you can actually accomplish multiplication by sliding the two rulers past each other. Okay, now luckily we don't have to deal with slide rules anymore. It used to be kind of a rite of passage that you would learn in your science classes how to use a slide rule because that was how things were done in the days BC. That's before calculators. Now that we have calculators, we don't really need to do that anymore. However, it's still useful to be able to do manipulations of algebraic expressions involving logarithms using these properties. So here we go. This is the product addition property of the logarithm. Now, just like you can do logarithm of multiplication and get something useful, you can do logarithm applied to division and get something useful. Here's the algebra behind that. I'm going to start with e to the m over e to the n equals e to the m minus n. That's just a property of exponents. I'm going to do the same change of notation that I did on the previous slide and replace the e to the m with a u and e to the n with v. I'm going to replace m with natural logarithm of u and n with natural logarithm of v. So that equation, upon replacing things as I've described, gives you u over v equals e to the ln of u minus ln of v. And all of this stuff, the ln of u minus ln of v, is up in the exponent. Be careful when you're writing things involving exponential functions, because it's an easy mistake to let something kind of sag and fall out of an exponent, and that would just be bad. From this second equation, boy, it doesn't want to highlight, does it? From the second equation, I can now apply ln to both sides. So u over v becomes ln of u over v. And then ln will undo this e and leave just the stuff up in the exponent. And that takes us here to ln of u minus ln of v. So in other words, ln of u over v comes apart into ln of u minus ln of v. I can show you that on the slide rule as well, because again, the distance from the 1 all the way over here at the beginning of the d scale all the way over here to 6, that length is the logarithm of 6. From this one on the c scale all the way up to the 3 on the c scale is the logarithm of 3. So I can think of this position of the rulers in terms of subtraction as saying that the logarithm of 6 minus the logarithm of 3, so now I'm looking backwards down the rulers, should be logarithm of 2. So this property is really very closely related to the addition and multiplication property that we did on the previous slide. Finally, we get to the power multiplication property. So for this, I'm going to start with e to the n as a group to the power m, and simplify that using rules of exponents to get e to the m times n. This time I'm only going to replace part of the equation. I'm going to let v be e to the n, so ln of v equals n. I'm going to replace e to the n here with this v, and then I'm going to replace this n with ln of v. Now I'm going to apply ln to both sides of this equation. On the left I get ln of v to the m, and on the right I get, well, the ln undoes e to a power and leaves just the exponent. So on the right I get just m times ln of v. This is power multiplication property. It is converting a power of v, the mth power of v, into multiplication by m. This is a little trickier to see on the slide rule, but there is actually a way to do it. Let me line these things back up again. So I had told you that the C and D scales are how you do multiplication. There's also A and B scales. These are up at the on the upper rod and the upper the top of the sliding part. And what you can see there is that it's very much like the C scale and D scale, except that A goes from 1 to 10, going over only half of the length of the slide rule. And then it goes from 10 to 100 over the rest. And the scale is abbreviated. So over here, this second 4 actually means 40. Now what this means is that I can use the A scale and B scale to calculate squares and square roots. Okay, so if I think of the length from A equals 1 to 4 as being the logarithm of 4, you can see that if on the C scale, that goes from 1 to 2. Well, the numbers on the B scale, seriously? Numbers on the B scale are squished by a factor of 2. So what you're seeing here is that 2 to the power 2, the 2 on the C scale, to the power 2 translates into 4 on the B scale. If I go to 3 on the C scale, 3 to the power 2 translates to 9 on the B scale. And if I go up to, say, 5 on the C scale, that translates to 25 on the B scale. So because the B scale is basically going twice as fast, it's increasing twice as fast over the same length, it accomplishes power 2. You can also go the other way. So if 2 squared is 4, looking at 2 on the C scale and getting 4 off the B scale, the square root of 4, you read you line up the 4 on the B scale with the 2 on the C scale. And same sort of thing here, square root of 9, I line up the 9 on the B scale with the 3 on the C scale. And then I could go up, let me see if I can find the 16. There's 15, so this must be 16 on the B scale, and that translates into 4 on the C scale. What's happening there is that we're using the fact that ln of v squared is 2 ln of v. Or you can think of it, ln of v to the 1/2 is 1/2 ln of v. So by having two scales, one that's growing twice as fast as the other, we can calculate squares and square roots. So again, this is not something that people generally rely on for actual calculations these days. Instead, what we're really interested in is manipulating algebraic expressions. And so in the next video, I will give some demonstrations of manipulating algebraic expressions.